Thank you again for joining us for our third statewide Master Gardener training. We are moving into soils tonight. We have Becky Young, who is a professor of practice here within our department. She teaches the Introduction to Soils class, so she's going to be perfect for getting you guys going. We do have Slido, so we are going to start the Slido. And your first question here, I need you to all join slido.com, number 4593. And your first question this is your first question. Which of the following is a soil physical property? Looks like you guys are all answering. Excellent. It's moving. So clay content is the correct answer. It looks like most of you got that. Excellent. Here's your next question. Which of the following is a soil chemical property? Pretty overwhelming response to soil pH. So, excellent. You guys are doing great. Next question. Which of the following statements regarding soil productivity and soil fertility is most accurate? A little bit more to think about on this one. Looks like soil fertility is the one thing that affects soil productivity. It's the biggest answer right now. All right, let's check it and see. Excellent. Becky can just go home. You guys don't need this. Next question. How much of a 10-4-7 fertilizer should be used if 28 pounds of phosphorus are needed? Little math in the brain. No cheating with the calculators. Looks like 7 pounds is the biggest answer so far. Yep, looks like 7 pounds is the biggest answer. Keeps getting bigger. Let's check. 700 pounds of fertilizer or phosphorus are needed. All right. So your last question for the pre-session questions. How confident do you feel about your previous response? How confident were you when you responded that? Excellent, excellent. All right. All right. So, all right. Thank you again for answering those questions for us. We will have a handful more here in a little bit. I did just stop sharing my screen. So Becky, you should be able to open up your PowerPoint on the computer in there and start sharing your screen. All right. It's all yours, Becky.
All right. Can everybody not in Lincoln see a full PowerPoint screen with a cute little plant on it?
Yes.
Awesome. Okay. I was like, I know how to do this, right? I was just doing this an hour ago. Okay, so I am Becky Young. I am a professor of practice, and what that largely means for me is I teach, and that's all I do. And what I teach is introductory soil science to about 150 students every semester. So I've been doing this since 8 o'clock this morning. So it's a good one. I usually don't do it all in one day or in 2.5 hours, but I've whittled it down to what I think is probably the most important, relevant to this particular group. So it's a little bit harder when I have 150 students who all want to do 150 things with their lives, but they're all going to be using soil. So a little bit of background. Again, I'm a professor of practice, so I just largely teach. I do research for fun, I guess, sometimes. It just kind of happens. I am not from Nebraska, so those of you not in Lincoln, if you have questions, if you can preface them with where you are relative to where you are in the state. Region works better than the county name because I only know a couple. So I'm from Wisconsin. My undergraduate degree is in physical geography, so it's not too far off of soils, and that's where I kind of got my interest in soils. Is my advisor did soil research with soils and landscapes and how landscapes change over time and how soils develop. So that's how I got kind of started. And then I came here for grad school, and I stayed here for grad school, and I stayed here to teach people going to school. So mostly what I do is I teach introductory soil science, but then I also co-coach the soil judging team. So that is an experiential like class kind of team event that we do. It's highly competitive in the sense that we just get really competitive about describing soils. So it's a great class to actually get students outside. We go outside for a whole week to a different place in the region every fall, and then in the spring we go to like a national contest. So there's in the fall maybe like 10 schools that compete, and the students get to stay out or be outside and look at soils in pits and describe them and classify them, and then they get to see those landscape relationships and land use relationships with their soils too. So it's pretty much my favorite class. It's why I do what I do, so I can keep doing that. So they're actually going to go to Ohio in April, so kind of exciting. They got 3rd nationally last year, so I was pretty proud. I was like, oh my God, you're amazing. So yeah, I really like soils. I've been gardening with my grandma since I was strong enough to pull the carrots out of the ground kind of thing. Did I think I was going to be a soil scientist when I was 5? No. But that's where it got me. So I really enjoy hands-on stuff, practical things. I'm a gardener, and if you ask Terry, she saw a picture of my garden last year. Just because I'm a soil scientist doesn't mean I'm a good gardener necessarily. So I am one of those people where I have to figure out how to apply what I actually teach to my own backyard. So, all right. So I have some more slide-do questions that I want Terry to share. And it's more of now to see, so you guys are really good at like what's a physical property, what's a chemical property. We'll work on the math part a little bit today. But then looking at some of those properties in more detail, like what would you rather have for a soil? So kind of testing your base knowledge in a little bit more detail now. So I'm guessing, Terry, I need to stop sharing my screen. Correct?
Correct.
Okay. So I think it's just 3 questions about which would you rather have for your soils. Okay, so our first one, which would you rather have? The best soil texture for growing plants. If you think about density, how easy it is to work, the water it can retain, and also how it drains. What do you think the best texture is? Excellent. Yes, it is silt, loam. So we'll talk about texture. I feel like that's one of the properties that's more commonly known with soil. We'll talk about why it is the best texture. All right, so which would you rather have for a thicker, more fertile topsoil, a soil that formed under native grassland, native deciduous forest vegetation, or native coniferous forest vegetation? Ooh, nice job. Yes, native grassland soils, so good place to be, right, is Nebraska for that. Nice, thick, dark topsoil. All right, and then what about for fertilizing a potassium deficient garden, but you have sufficient nitrogen and potassium? Do you want a complete fertilizer with nitrogen, phosphorus, and potassium, because more is always better, or a single potassium fertilizer? Woo! Nice, unanimous. That's what I like to see. Because more is always better when it's ice cream and chocolate, right? That's when it's good. So we'll get to the fertilizers more towards the end and talk about why that is, why we don't want to over apply certain things, especially nitrogen and phosphorus, which are necessary nutrients and very common, but we have to be careful with them a little bit. So. All right, so we're just going to start with the basic, what is soil? And I'm sure most of us know what soil is, but kind of looking at it in a little bit more detail. Let's get a little bit more specific about it. So when we think about soil, it's the stuff that our plants are growing in, but if we had to define what it's made of, it really has four main components. It has mineral material, so that is the tiny little particles that are broken down from rocks, so made of quartz and feldspar and iron and aluminum oxides. We have pore space, so where the solids don't exist, so that's where our air and our water are going to be, and we need that, right? That's kind of what makes the soil like a sponge. And then usually what gives the soil the dark color near the top is the organic matter. So those are organic residues that are broken down from the plants and are serving as food for the microorganisms and nutrients for our plants. So we have some solid components, some liquid, some gases. So your soil should have all four of these. A good ratio of these would be about half of your soil is solids, half is pore space. Because otherwise you don't have enough space for your water to exist, right? So we want to make it a nice sort of loose, not too heavy of a material for your roots to grow through. And what would separate soil from dirt then is the fact that it can support life. So that's what we kind of teach our students, is why, you know, we don't like to call it dirt, because dirt is a very dirty word. It's, we use it, we throw it around quite a bit. So soil, we differentiate, it can support plant life. So it's what we would grow the plants in. And then we tend to focus on the topsoil when we're growing plants and gardening. But one thing to think about is that that soil wasn't always like that. So soils also show a change over time compared to the original sediment they started with. I really like soil formations though. I always like starting with this stuff. So the change part always gets me really excited. It's a really slow process, but if you think about it, it's fascinating, right? Awesome. Soils change. All right. And then I always have to get my students like excited about soil, right? Why are we talking about soil? Well, it's one of those components that it's a nice interface between the living component of our earth, the air, the water, and the rocks, right? It's where it kind of all comes together. And if we didn't have it, we wouldn't be able to grow plants and support ourselves. So it provides water, nutrients, oxygen, mostly to our plants. It provides surface stability and structure for growing, or not growing, building houses. It'd be fun if we could grow houses though. And it just provides like a nice medium for our water to move through and become filtered. And one of the things I try to impress upon my students is that we use the soil a lot, and it is resilient, but it's on a scale that often doesn't match up with human activity, right? It's not inexhaustible, but it takes a long time to bounce back if we don't give it the right kind of care. So, all right, so most of the time when we are dealing with the soils, we're usually dealing with the topsoil. So it kind of looks fairly homogeneous. What I really like about this year versus last year is it's February. Usually there's snow outside and the ground is frozen. So I can't really take you outside in the dark, in the winter, in the cold, to a soil profile because I can't dig it. But in the summer when we have a field day, we have a teaching pit on campus. So we can see what's below our topsoil. And that often has a greater effect on deeper rooting plants and also structures, right? If we build a house into the soil. So mostly what we deal with is the surface or the topsoil. So that'll be our A horizon. It's fairly dark from the extra organic matter that moves into the soil. It tends to be a little bit looser because of that extra organic matter. Our subsoil, our B horizon, that's also a part of your soil that's changed over time. It might have a different color. It might be a little bit clayier because the clays are small and they move down with water. So you have usually a slowing of water flow through your profile when you get to the B. And that can affect your plant growth, like how easily it ponds on the surface. And then deeper in the profile would be your parent material, so our C horizon, right? Soil scientists don't like to make it too complicated. A, B, C, right? You just go down your profile. So your C horizon would be what is relatively unchanged. So that's your picture to the past. So at one point, your whole profile looked like the C horizon. And then with additions of organic material, water moving through the profile, stuff breaking down and oxidizing over time, your two upper horizons developed, right, in place. Those weren't added on top. So they have a lot of the inherent characteristics of your parent material. So if you know what your parent material is, you already have an idea of how useful your topsoil is, even if like the picture of your parent material is down at the bottom, right? You don't have to dig that deep if you know what your parent material is and your location. And there's maps for that. We'll just look at one shortly. All right, so why aren't all soils the same? All right, everybody says, I can say this, I'm not from Nebraska. Everybody's like, Nebraska's flat and boring. And then you come to Nebraska and you're like, no, it's not. It's actually very diverse. We have a lot of variety of soils in Nebraska. Surprisingly, we have more than a lot of other states of similar size. And it's all thanks to all of the unique landforms we have going on in the state. So why you have different soils, even though they're similar, there's really distinct differences in them in Nebraska. Differences in climate. So how much water is moving through your profile. It's going to change the rate at which processes occur. Same thing with temperature. And also things like organisms, what's growing, what's native in your location. It's going to influence what kind of nutrients go into your soil, how quickly your organic matter breaks down. Your relief or topography. Are you on a flat location? Are you on a steep location? Is it close to a stream? Your parent material, which is what we were just talking about, those are kind of like your built-in characteristics and what you have to work with. And then time. Our last one is stability with time. Not necessarily how long it's been there, but how long it's been unchanged, like it hasn't been active. You haven't had erosion or interruptions in it being able to change over time. So of course I have an acronym for this because I like fun words. So all together, these would be our 5 soil forming factors. So why we have, thick topsoils here versus in northern Minnesota. So my acronym is CLORPed. There's your fun little word for the day. So you have climate, organisms, relief, parent material, and time. And some of these will be more distinct than others with your soils. And We have a few really distinct characteristics with most of Nebraska soils that stick out related to a couple of these, which we'll talk about shortly. So first, let's kind of look at climate. And it looks like my animation's not working too well, but you'll get the gist with the Nebraska map. So with climate, we're usually thinking about temperature changes and precipitation, specifically how it moves into the soil with water. So temperature, it kind of changes more north to south. It's warmer more consistently to the south. Here we have cold winters and hot summers. If we move to the north more, we have cold winters, shorter summers. So the temperature often will just more affect your plants than it will the soil. So climate and organisms are hard to pull apart. But precipitation, you tend to see more distinct changes with those. So in Nebraska, because we're kind of on the edge of the rain shadow, it's much drier out in the western part of Nebraska than it is in the eastern part of Nebraska. So what you end up seeing as you go across Nebraska, if you got a profile from each point, is your topsoils get thicker as you go across the state. And then digging down through your profile to get to the parent material, you have to dig further and further and further because your water is breaking down materials in your soil. And if you have more water, it can go deeper in your soil. So you get really thick sort of soil profiles with darker colors, brighter colors, because you have more changes because there's more water in eastern Nebraska than western Nebraska. My animations are underneath the map. That's awesome. All right, so what you might see is something like this. Maybe in Arizona where it's really dry, like a desert or even like a dry Arctic condition. We do have soils in those locations, but not a lot going on. Very thin profiles. Bedrock might be very close to the surface. And the only noticeable thing you might see is just a little bit of color difference at the surface. But then as you move into something that's a little bit more semi-arid, like western Nebraska, you start to see a topsoil. It's darker brown. Your subsoil is starting to develop because you have water movement deeper. But your bedrock is still, within a meter of the surface in some cases. It's just an example. You move to west or eastern Nebraska, and now your topsoils are getting thicker. They're darker because you have more plants can be supported by that precipitation and that more humid climate. Your B horizons, I don't know if you can see the color, they get brighter a little bit. You have more oxidation of iron with the wetting and the drying. And then as you start to get to Georgia, right, if anybody watches TV shows that take place in Georgia or have been to Georgia, your soils start to look more red. I mean, I was trying to be nice with the color here. I didn't go too crazy, but they really start to oxidize. And then as you get to the tropics, even where it's warm and humid all year round, they're bright red because everything just happens so fast. And the only thing you're really left with is oxidized iron in your soils. So the more water you have, usually the deeper your soil gets, your topsoil can be a little bit thicker. But we, thankfully, in Nebraska, we're in a nice location with moisture. It's not too wet. Some places are drier than we would like them to be. But that's what irrigation is for, right? We can amend some of that. So, all right. Our next forming factor was organisms, so vegetation. And vegetation is the dominant part of organisms. What type of vegetation is native to your location? What kind of nutrients is it adding, and how easily does it decompose? Some soils you'll have distinct patterns in them. You might see some mixing or some burrowing because of insects or animals. And that's good. It moves your nutrients around. It can move them deeper. It can loosen up your soil. But it really kind of goes back to your vegetation. So those organic matter inputs, how much kind of dies and decomposes each year and gets added back into your soil? How easily does it break down? What's the chemistry like? And does it get mixed? So the greatest thing with your organisms is vegetation. That's why I had a question about your topsoil earlier. So the two types of vegetation we have close to where we are. The most dominant one is grassland, right? Native grassland. What is the native organism, vegetation of Nebraska? Grass, 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 grass. Short grass, tall grass, mixed grass, tall grass. So it's going to have a very similar effect, whether it's tall grass or short grass, compared to trees, in that it's going to make your topsoil thick, which is good, right? That's where it's going to hold a lot of nutrients. It's going to have a lot of organic material, which holds on to water. It'll soak it in like a sponge, which is great. And this is all because with a grass versus a trees, your biomass is already in the soil. So when it dies and decomposes, it doesn't have to get mixed in. It doesn't just sit on the top. The organisms can break it down in place, and it's there already. So it breaks down more quickly. It's usually a little bit of a drier climate compared to your deciduous forest. So your organic material breaks down very quickly. And a deciduous forest, if we think about in the fall, all the leaves fall on the ground, and they just basically sit there. So it takes more work and a longer time for your leaves to break down and get mixed into your soil. So you end up with thinner topsoils than you do compared to a grassland. So, whoo, Nebraska, yes, thick, beautiful topsoils, so thick. I grew up in deciduous forest land, not that thick, right? I was close to the coniferous border even in Wisconsin, and once you get up there, very, very thin. And it's because those needles break down even more slowly than the leaves. All right. Oh, hey, look, I had notes on here and everything. I get so excited. But I put the notes on there for you. I know what I'm going to say, but this helps you guys follow along a little bit faster. So, all right. So you guys know it. All right. So our next one, because we got some good stuff to get to, is topography. And I have a feeling most of us are more familiar with topography and little changes in our landscape, in our backyards, because Nebraska is not flat. If anybody says that, take them out to the sandhills, even southeast Nebraska, it is not flat. Get them off the interstate. So you're going to have more erosion on steeper slopes than you will on flatter slopes. Whether it's arid or humid, it's going to happen in both cases. Because in arid regions, you're going to have less moisture because your water is going to move down or just not be there. So you have less plant cover, less stability holding your soil in place. And in humid regions, you have more water moving over your surface, carrying your particles away. So on your back slopes, on your steeper slopes, you end up with shallow profiles, so thinner topsoils. So they can be harder to work with because they might be closer to bedrock. You might have unstable things underneath that, really close to the surface. So we like to be on the summit, at the top of the hill where we can look out on our beautiful landscape and plant very stable things. But we're not all gifted with that, right? My backyard has a very steep slope, and it's been a challenge. So we put in a raised bed, right, to even out our slope in the back. The toe slope at the bottom of the hill, also flat and stable, makes it easy to work with. But that tends to be closer to a river on a lot of cases. So that can flood pretty easily. Plus, whatever is coming down your back slope is getting piled on your toe slope. So if you have a very quick erosional event, that might be very disruptive. And you have to kind of start the soil forming process over. All right, so your profiles might look something like this, where you have, on your flatter parts of your landscape, really sort of thick profiles, deeper development, nice topsoils to work with. And on the back slope, you're going to have something that's more shallow. You might be thinking, well, that toe slope looks pretty good, right? It's pretty dark, but it could easily be flooded, right? There's other issues with where it's located. It might be saturated as well because it's low on the landscape, so the water table could be high. So our best place ideally would be the summit, but we will generally take anything that's flat, and if it's not flat, by golly, we will make it flat if we have to. right? Because erosion is going to be one of those issues is what we're dealing with, trying to combat and control the most, that we'll talk about at the end. All right, parent material. This is the one I get the most excited for because I'm like a geology soil scientist. Oh, I love it. So parent material, that is your natural sediment that stuff is forming in. I like to think of, past climates and really big windstorms that are blowing the sandhills around, and the sandhills, oh my gosh, the sandhills, they're so beautiful and they're full of sand. I know, amazing, right? I love it when names are very obvious. So we already know what makes up the sandhills. It's a lot of sand. If we've been to the beach, if we've played with the sand, we already have an idea of what problems that presents with our soils, right? They drain water really quickly. They don't hold a lot of water or nutrients. So those are some of our inherent properties, our physical properties and chemical properties that we have to work with. And then as we get more towards the eastern part of Nebraska, we have loess in the blue area. So that's windblown silt. So it's a smaller particle than sand. It's a nice medium-sized particle. Often has silt loam textures at the surface, which everybody says was the best texture. Nice job. Yeah, exactly. So it's a nice kind of medium where it doesn't hold too much water, but it doesn't drain it too quickly either. And it makes like a nice rooting bed then for your plants. Nice medium-sized spaces. This is a map I use a lot. So the red star is where Lincoln is. And you'll notice that Lincoln is near this area in pink, where at the surface we have glacial till exposed. And I'm like, man, I like talking about glaciers. I really do. I think they're great. But they leave some hard to manage material behind because they don't sort it into different sizes of particles. So you have these very dense kind of clayey materials to work with that also have rocks in them. And you're like, why? Why do you have clay and rocks? Why not just one or the other? So we have different ways we have to manage these soils because some are really dense and clay and hard to work with. Some are just very sandy and they react very differently. And then your parent material, again, is going to give you some of those inherent properties. So even if you have those development of A's and B horizons in your soil, it's still going to carry over a general texture throughout the profile. That's not going to change much. And it's going to kind of control your range of chemical properties natural to your soil. So you might have an idea of like a starting point with your nutrients and what it's going to hold in your soils if you know your parent materials. And then I like that you can really see where all the rivers are in Nebraska, right? So the flooding, it's going to move whatever material is kind of upslope from the river. When it floods, it just deposits it right on to the floodplain. So if it's a smaller stream kind of moving through the loess hills, or the loess plain rather, it's going to be eroding silty material. So when it floods, it's flooding out silty material as well. It depends on the flood event, obviously, how fast your waters are moving or how slow, because you can get very different sediments at different times. So living on those lower parts of the landscape, you tend to have a little bit more activity going on with your parent material. So, all right, moving on, one more. I get so excited. Okay, so your parent materials, let's look at some of the common ones in Nebraska, because they could be bedrock as well. It could form in place. A lot of our soils in Nebraska have been moved in by some sort of process, like aeolian sand. Those are some winds that move in that sand. Because it's so sandy, it doesn't hold water, it doesn't hold a lot of variety of plants either, so it doesn't add a lot of nutrients. You get a very simple profile. Just a little bit of color at the top where your plants are, not much after that, right? Throughout the sandhills. And then as you get more towards the streams, you might notice there's a dark band lower in your profile. So because you get a lot of additions and deposits of material in the streams, that's actually adding new sediment on top of a profile that could have been there already. So especially like this last spring when we had a lot of floods, I noticed my students are mostly farmer students or farming students, and they would send me either pictures of really eroded fields, or they're like, we have so much sediment that wasn't there before. So their fields are probably like this, if you dug a hole or a profile through them, where now they have a whole new batch of material on top that wasn't there before. And it might be stickier or it might be sandier than what was there. So now they have to figure out how to use it again. But if you have something that's a little more stable, like bedrock, which doesn't really move, I hope, and it's going to break down in place, you get a very general kind of profile. And it can be fairly deep if you're in a humid climate. And again, the type of rock is going to determine how easily it breaks down, what kind of texture it has. So shale, which is really common up in the northeast part of Nebraska, especially along the Missouri River, it's a rock that's made of clay, basically. So really fine particles. So you're going to have really clayey soils as a result. If it were sandstone, you're mostly going to have sand, right? So yay, sedimentary rocks. They're the best rocks to work with. All right, so this is going to kind of lead us into our physical properties here shortly. So our parent material kind of tells us what our texture is going to be like, how easy it is going to be to work and deal with, water movement, and then also maybe some inherent properties with the nutrients a little bit later on. All right, our last one is time. And similar to like what we were just talking about with the floodplains, the more you leave the soil alone, the better it develops. So the thicker the topsoil can get, the more organic rich and nutrients it can start to store. So really sort of young soils are those that don't have a lot going on in their profiles. And because we have more humidity on this eastern part of the state versus the western, you have maybe some thicker parent materials that hold more water. The soils on eastern Nebraska tend to be more on the mature side versus the sandhills are more on the young side because they're fairly young parent materials and they just don't develop that well. So yeah, so you can talk about your soil like, I have a pretty mature soil. That soil's so young, it doesn't know what it's doing. But the very mature soils, those are going to be things that are maybe a little bit more to the southeast in the United States, where you have thicker development, warmer temperatures, so it can, and more humidity, so they can develop deeper in your profile and more distinct layers and bigger differences in your horizons compared to the parent material as well. All right, so a lot of us though are gardening not out in natural settings anymore, right? A lot of us are gardening in cities or towns where we've had our natural landscape disrupted. We've bulldozed the land so it's flat. So oftentimes the topsoil that you want to have for your gardens, for your plants, is gone, the natural topsoil. So it's been disrupted. You might have some subsoil that's right at the surface, so this really light color. And if I see that, I'm like, oh no. And then sometimes though, they'll backfill it with topsoil from somewhere else. And in that case, you don't know where it came from. You have little control over what it is like. So it's more difficult to manage city or urban locations and gardens because the soil has changed so much. It's been disrupted. And oftentimes we have to bring material in and we don't really have a lot of control of what went into the material in the first place. So we'll talk about that more towards the end, and some of the issues that go with that. So, all right, soil physical properties. I've been talking about this stuff for a month. I'm so jonesed. Yeah, when we get to soil chemistry, that's the stuff I start next week, and I'm like, oh man, I haven't looked at that stuff yet because I haven't talked about it in class yet. So, soil physical properties. I think these are the ones we're a little bit more familiar with because it's when we touch the soil, it's when we feel the soil, it's when we see how the water moves through the soil. So those are all the physical properties in our soil. So kind of getting back to your composition, we kind of looked at this at the beginning. Ideally, half of your soil material would be solid. And of that, about 5% organic matter at the surface. you might be like, well, the topsoil is really dark. It's almost black. Just a little bit of organic material adds really dark color to your soil. And 5%, that's fantastic. It doesn't really have to be much higher than that for growing plants. So then the rest of that would be kind of your mineral material. So that's going to be your sand, silt, and clay particles, the stuff that gives it grit or substance. And then the other half of your soil would be pore space, so the voids. And that's really important because ideally about half of that pore space is air, so you can have respiration of your roots and space for your microbes to grow and live and breathe. And then the other half would be water. But not all water in our soil is what the plants can take up. They can only take up certain types of water, certain amounts of water. And it's going to be the water that's in medium-sized pores or large pores. Because in your very tiny pores, it's held so tightly by the soil particles, the plants spend way more energy than they can actually spend to pull up that water. So you'll have some ratio of unavailable water. All soils are going to have that to available water, but the ideal would be that half of that water is available. All right, so our biggest physical property, if you had to know one physical property about soil, it would be texture. Because your texture can tell you a lot about your soil. You can make a lot of inferences and come up with some expectations about your soil just knowing the texture. So your texture is how much sand, silt, and clay. What are the proportions of those in your soil? How fine or coarse is it? How gritty or smooth or sticky? And there's two ways we can do this. You can do it by feel, which some of you might have done this before. It's making a ribbon with your hand. And if you come to the field day, here's my plug for that. We will do this, and it's fun. It's great. I love it. Or Terry set this out for me as well. You could do it with a jar test. So this is kind of similar to how you would do it in a lab, where you suspend it in water, and then because your sand is bigger and it's heavier, it falls out first in the water when the water stops moving, and then your silt, and then your clay. So you end up with layers of particles in your jar. And if you measure the heights of those compared to the total, you'll get your percentages. So in our soil, sand is the biggest. You can see the sand particles in your hand. They feel really rough. It feels like sandpaper. My students are like, oh yeah, it would. I'm like, yes, it would, because sand. So you don't need any assistance seeing the particles. They're that big. So imagine you have a dinner plate in front of you. That is your sand particle. The silt particles now are going to be a cracker crumb on your plate. They are much smaller. They are going to feel smooth and light and flowery. It's the thing you want to feel in your soil because your hands don't have to work hard on it, and it doesn't. It's not coarse on your fingers. So it feels really light. It's easy to move. You might need a microscope to see the finer parts of silt. A hand lens is okay too, to see the larger sizes of those. It kind of leaves an imprint if you put your finger on it. It's kind of like really, if you just had flour when you're making cookies or cake and you got it wet, that's what pure silt feels like. It's really nice and fluffy and light. But that's the cracker crumb on your dinner plate. And a clay particle now is a tiny little piece of iodized salt on your cracker crumb. So much, 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 much smaller. And they have a different shape to them as well. Sand and silts are round, but clays are flat. They're like pieces of paper. And they stack on top of each other so they stick together more. And this you do need a microscope to see. It's very small. And because of that flat structure, it's very slick and slippery when it's wet. So it's exactly like modeling clay in school. It feels a little bit more like silly putty or Play-Doh, where it's a kind of a smooth, kind of sticky material. Something I joke with my students about, just to see if they'll do it, is if you really want to tell if your soil has silt in it, if it feels really smooth and kind of sticky, you can put it in your mouth. And the silt, you'll feel it when you rub your teeth back and forth because they can pick up on that little bit of grit that your fingers can't. And my students are like, I'm supposed to put this in my mouth? I'm like, you can if you really want to. I don't recommend it, but I'm just like, that's what the more geologists will do, I guess, to see how much silt is in there. I just like to do it by feel. I don't like to do it with my mouth. So those are kind of the things to think of when you're texturing or trying to feel your soil. Does it feel really gritty like sand? Is it kind of like flowery and soft, or is it really dense and sticky like silly putty? And often you're going to have a mixture of those in your soil. So it's kind of figuring out what is the dominant feel in your soil. All right, so then what you would do if you know about your ratio of sand to silt to clay, your percentages, you can use the texture triangle and give it a class. So the way to read the triangle is on the bottom is the percent sand, on the left-hand side is the percent clay, and on the right-hand side is the percent silt. So you'd find the number, the percentage on each side, follow the lines that they're next to where those points meet on the triangle, and that will tell you the class. Generally, the bottom left-hand corner is where the sands are the highest. So it's a really coarse materials. So think really fast drainage, doesn't hold a lot of water, doesn't really stick together very well. The bottom right-hand corner and kind of like a lower band across the triangle there in the green is your medium textures. So these are mostly silty soils, or if you move to the middle of the triangle, a little bit of sand, a little bit of silt, a little bit of clay. So it kind of averages out to medium. So those are the good ones that are easy to work with. Those are the best ones for your plants because they don't hold too much water, but they don't drain too much water either. And then your fine textured soils are the clays near the top. So those become harder to work with. I don't know about you guys, but I'm really not looking forward to digging through my garden this summer because we have a lot of clay in our raised beds because it's one of those things where you can't really control the fill you get from an excavation company for topsoil. So it's harder to work with those soils and they hold a lot of water, but we have ways to work around that to make them better and more manageable. So if you know your texture class, right, just think about all the things I was describing. You have some ideas about drainage, aeration, how much water your soil can hold, how easily you might have erosion occurring if you have a steep slope. So the smaller the particle, the easier it is to get picked up and moved away. And then fertility as well. The clay particles are what hold your nutrients in your soil. So those are the storage sites that hold them in place and have exchanges in your soil. So the more clay you have, the more fertility, more fertile nutrients you might have in your soil as well. And again, the ideal is the silt loam. We're kind of winning in Nebraska. A lot of our soils tend to be in the medium textures, kind of naturally silty, until you get into the more different parent materials like sand in the sand hills and like the really clayey sort of tills as well. All right, so again, you can do this by feel. There is a ribboning method. There's lots of videos for this online. I recommend looking at the NRCS videos because that's the Natural Resource Conservation Service. And how I recommend like learning this is practice on textures that you already know. So like, what does a sand feel like? What does a silt loam feel like? And then that way you get kind of like calibrated to how those work in your hands because everybody's hands work a little bit differently. But there's a flow chart that you would follow. So when you're making a ribbon, you kind of look at how long it gets before it falls out of your hand. And then is it gritty, smooth, or a little bit of both? And then it puts it into a class for you. So again, on the field day, this is something that's easier to do when you're not in a classroom with carpeting because it requires water and towels and soil gets everywhere. So this is a very much an in the field kind of activity. The one I gave you instructions for is the jar test. So in this case, you take a mason jar, about a quart. You put in half a cup of dry soil. You want to get rid of the moisture. Crumble it up as small as you can because then you want your particles to be distributed. And then you put a little bit of borax or laundry soap in there because there's sodium in that. And that causes your clays to not stick together. So that's why you put that in there. Because if they stick together, they're going to be a big clump and then they're going to fall fast and you won't get a good reading. So then you just kind of shake it up real well, distribute it, and then you let it settle. You get the full height of your sediment and you shake it up again. And then at certain times, after about, where is it? I'm reading the instructions. After about 40 seconds, the sand will fall out. So you should be able to like shine a light through it and see a nice little layer at the bottom. So you can measure the height of that. And then that will give you your percent sand with a little bit of math. And the NRCS has a soil texture calculator. So if you have your depth, it'll automatically put the percentages. It'll do the calculation for you. And then you can determine what your texture class is on the triangle. I think it tells you the class as well. So I put an example on the instructions on the back of what that might look like as well. So I know some of you might have brought a jar with you, and you can do this on the field day as well. You can do as much as you want. But yeah, all you would need then is a ruler to measure the different depths and stuff. And I recommend doing that maybe during the break or something, getting up and kind of shaking it and see what happens, because it only takes a few minutes. And then the second one, it has to sit for 2 hours. So it'll be done by the end. It'll be great. All right. So texture by feel, I just kind of wanted to walk through it. Again, you just add some water. You see, does it keep a ball? If it doesn't, it's probably sand, right? Sand doesn't stick together. And then you just kind of push it between your fingers and create what we call a ribbon. And you keep pushing it until it breaks. And when it breaks, then you measure how long it is. And the longer it is, the more clay you're going to have. So the higher you're going to be on the triangle. And then it's just what part of the triangle, how left or right are you? If it's really gritty, you're going to be more on the left side of the triangle. If it's really smooth, more to the right. If it's kind of both, you're in the middle. So again, there's a lot of like flow charts that kind of go through how to do this really well. So the key thing with this though is making sure when you're getting your sample ready is you break up the aggregates. You make it as smooth as possible, like silly putty, so you don't have clumps. Otherwise it'll break off early in your hand. So I see a clump in that ball. I don't like it. So all right, so again, the jar test, it's pretty straightforward with the instructions. So for example, if you ended up with having a 10 centimeter depth of soil in your jar, and after about 40 seconds to a minute, 1.5 centimeters was sand, 5.5 centimeters was silt, and then 3 centimeters was clay, you'll end up with 15% sand, 55% silt, and 30% clay. And then on your texture triangle, when you put all those numbers together, it's a silty clay loam. So it's kind of over on the right-hand side. It's still in the medium texture, so it's a little bit more clay than our ideal texture, but that's okay. It's still very usable. It's one of my favorite textures because, of course, I have a favorite texture because it's the one that doesn't hurt my hands very much. Yeah, it's great. My hands get really tired after texturing a lot, so I really enjoy that one because it's easy to work with as well. All right, if your water doesn't clear out, that's okay. Because I'm guessing that if you've taken your sample from your garden, it's going to have organics in it. So it's going to stay in the water, and you might have material floating, and that's your organics. They're not going to settle out very well as well. So it's very rare that it's going to be completely clear. All right, hey, look, there's a texture triangle. Should we see how to use it? There you go. So the sand, how you would follow that on the bottom, it's not very intuitive. So it's nice to have a visual. You find the number on the bottom and you follow it up to the left. The clay just goes straight across and the silt comes down to the left on your triangle. Okay, so the sand and the silt kind of go inward towards the triangle and the clay just goes straight across when you use it. Okay. And this is something like we can chat about during breaks or on field day, or you can email me too. That's always great. I like talking over Zoom. This is fun. All right, so if you know your texture, again, you can figure out a lot about your soil, like how much airspace it might have because of how much pore space it's going to have, how much water it can hold, how easy it is to work, and then compaction as well. So that's an issue in urban locations. So those really fine particles have more space, more void space in them because there's more of them in a volume. So they compact more easily than sands will. Sands are more rigid. They don't move a lot in a volume compared to clays and silts. All right, another thing you can look for in your surface is your structure. Right, so structure is how your particles are arranged together, how they create a shape, how they stick together. If we didn't have structure, everything would be loose. And if you just have loose clay and loose silt, water is going to move very slowly through those. So in this case, when we pull up a plant, we often see clumps of soil hanging off of the roots. Well, that's the structure. That's how your particles come to stick together. When the roots are moving through the soil, they're pushing the particles together. Remember, the clays are sticky, so they often clump together then when they're close together. And that's great because in your fine and medium textured soils with silt and clay, it makes bigger pores. So you have better drainage in your soils that you might not otherwise have if you didn't have structure. So how you would describe structure is there's a couple of different steps to it. It's what is the shape of your aggregate? Is it round? Is it tall? Is it long? Is it flat? What size is it? Is it small? Is it large? And then how stable is it? So how well does it hold its shape when you put pressure on it? And what's holding your aggregates together? One could be clay. That's a cementing agent. Organic matter is like a glue in soil. So you tend to have pretty nice structure in your topsoil if it's not disturbed a lot. And then other things like calcium and iron are also fairly sticky in your soil. It can help hold your aggregates together. So in our surface, what we're mostly going to see is really small aggregates if we have a lot of roots. So it looks more like granola. So we call that granular structure. It's kind of rounded. It's very small. What you might see more in some other soils, though, if it's a little bit bigger, we call it blocky, where it's roughly the same height and width all the way around, but it has more of like a block, an abstract block shape to it. It's going to differ as you go through the profile. It gets bigger and taller, usually as you go down towards your parent material. But structure is important because if it's easily disturbed, its stability, it's going to move apart and it's going to destabilize, and you can get crusting on your soil as a result. When you have compacted soils, though, an indication that it has been compacted in the past, even if you don't see like tire tracks or something on it now, is if you have something that looks like stacked plates in your soil, because it's pushing everything down into layers. It's a little bit hard to see here, but if you can see those horizontal lines that mostly go across, that's an indication of compaction. So in that case, maybe tilling it is a good option to loosen that up a little bit more because it's going to be fairly dense. There is an app, which I might share the link with you afterwards. One of my former students just told me about this last Friday, and I was like, there's a soil app? We have apps? It's great. It's called Flakes, and it's super easy to do. So it measures your stability of your aggregates. So it tells you, if you get your soil wet, are your aggregates going to hold their shape, or are they just going to fall apart and create a crust? It's free to use. All you need is soil, plate, and water, and your phone. So I have a little video here. Maybe I'll let it run during the break. You would basically put your aggregates on the plate, and it takes image referencing, and it measures how big they are. And it saves that size. So you don't move your phone. You have to have something to keep it on, suspended above it. And then you take your plate, take the aggregates out, you put some water in, put your aggregates back in, and you hit a timer. And it runs for 10 minutes, and it watches your particles or your aggregates fall apart in the water. And it measures how much they've changed from their original size. I know, it's fascinating. I was really excited about it. And then at the end, it gives you a coefficient. So how stable your aggregate is. The lower the number, the better, because it hasn't changed that much. And it color codes it too, like red is bad. So the example video that I have, it's red. You can see those aggregates fall apart very easily. So it's super simple to use. I got really excited about it. I'm going to use it in my online class because I teach soil science online, which is super difficult because they don't get to touch the soil. But this is something anybody can use. It is so great. So I recommend playing with this at home after this because it takes time. We got time. We have stuff to get through today. So moving on. We should be able to get through our physical properties here, and then we'll take a quick break. So structure, again, it's important because it actually increases your larger pores, which helps your soil drain water if it's a really sticky soil, your clay soils, because those soils hold a lot of water rather than drain the water. So we want some drainage so we can even out our ratio of water to air after rain events. And it also provides more space for your roots to grow. Your microorganisms live in the pore space, so those nice symbiotic relationships. It makes for a better seed bed, so your seeds can push through when they're germinating as well, so it's not just a crust that they have to push through. But it's one of those physical properties that's really easy to change, because anytime you mix up your soil, you're going to break up the aggregates. They're going to get smaller, or they're going to just break apart completely. One thing that is a more common problem in arid areas and where you have a lot of salts, specifically sodium, is sodium. If you remember when I was talking about the jar test, it disperses clays. So having a lot of sodium in your soil keeps your soil from developing structure. So it's kind of like a back and forth. And then sodium's not a great nutrient to have a lot of in your soil anyway. So that can be a hard one to manage, but there are ways to manage that. The easiest way to fix your structure is add organic matter. So some compost, some peat, because organic matter is like the glue, it's sticky. So it'll help pull and bind your particles together. This is what I'm doing, probably this weekend. So if anybody wants to come add peat moss to my garden this weekend, you are welcome to do so. Because like I mentioned, the fill we got for our raised bed garden, because it's on a slope, it ended up being really clayey, but that's what they had. So we've had to add compost and organic matter to try and loosen that up and build better structure. We might even add sand at some point to try and get it a little bit coarser, but the texture is hard to change, but not necessarily the structure. And then both of these are going to impact your water, right? That's the one thing that can be tricky to do, is water your soil for your plants. So sandy soils have really big pores. They're really well connected. They're fairly loose, so it drains really quickly. It's like all of your pore space is interstate, right? Everything's moving fast and it's getting out of there. So we call those the macro pores. So they help facilitate movement, but we don't want just macro pores in the soil, because we want some of that water to stay there. Your clayey soils, though, are like a highly congested downtown New York, right? Very small streets, lots of water trying to get through all at the same time. So tiny little micropores, and they're going to hold water really tightly because of attraction to those soil particles. So those micropores are great for holding water, but we don't want just micropores. Otherwise, we're going to have saturated conditions, and the plant still couldn't access the water. So we want something in between. So ideally, a silty texture or improve the structure on our fine textured soils. Sandy soils are just going to be tricky to deal with, but organic matter could help keep some of that water there because it'll take in water like a sponge. All right, so this is kind of like a microscopic version of your soil. So example, a topsoil with really good structure, your particles are kind of tight together in your aggregate. So you have micropores there. You might have some macropores, mesopores between your aggregate. So you have some drainage, some retention. And then you have a lower bulk density, which is how many solids in your volume. So it's a lighter soil. It's easier to work with. You have plenty of space. In a poorly structured soil, though, you could see it's pretty tight. There's not a lot of big pores. They're all kind of the same size. In this case, if this is a clayey soil or a fine textured soil, they're all really small. So it's going to take the water a long time to get through there. So it takes a long time to drain and aerate, so back and forth. And then you also have more solids in that same space now. So you have a higher density. So it's just hard to work with. It's what a lot of people call a heavy soil then in that case. All right, so this is another one we might do this summer, but anybody can do an infiltration test. If you want to see what infiltration is like in your soil, you can get a metal ring. So for example, you could just buy a cake pan, a round one, and you push it into the ground and you fill it up with a certain amount of water. And then you time how long it takes the soil to take in that water. So you're kind of, controlling the volume of soil you're working with and the amount of water that you're using. And you can measure this over, a period of a day and see what your infiltration rate is like. So for sandy soils, you might have something that's like 20 inches per hour. A clayey soil might be 0.06 of an inch per hour, right? So there's a huge range there for infiltration. And just better aggregated soils will move it a little bit faster. So plenty of resources and videos on those activities as well. So, all right, and I think we're almost getting into chemical properties. Okay, I knew I had a couple slides left. So permeability, the very slow race, those 0.06 of an inch. I'm glad I remember my numbers. You see, I was just talking about this today. 0.06 of an inch, that's going to be a very clayey soil. So something in the moderate, though, that might only be 2 inches per hour, but that's good, right? That's a nice rainstorm, 2 inches of rain in an hour. But that's under saturated conditions. So that means it's kind of slow. It'll take up some of that water into the micropores and mesopores and store it, and then drain away the extra. Versus the very rapid, like what you might see in the sandhills, because it's predominantly sand, is it just drains very, very quickly. So, all right, and then compaction. I know we've kind of looked at this a little bit before. The really extreme cases of compaction tend to be the wheel tracks in fields, yeah, where you have a really distinct plate in your soil. So not only does that limit how your water moves in, because it's going to move very slowly, but it also limits gas exchange. That's another really important component with your pores. So it makes it harder for your microbes to live there, which is why they're often completely bare. And it takes so long to get any vegetation to grow back. So compaction is one of those things that's easier to avoid than it is to actually fix. Because it can be fairly deep if it's over a long period of time. So trying to keep the same paths, putting stones out and walking on those rather than walking over the same soil a lot is very helpful. So, all right, I think, Terry, is it a good point to take a break here before we get into chemical properties?
Yep, I think so. We'll get everybody to stretch their legs. You're good to go.
Okay. So moving on to some of the chemical properties, I think this is what we tend to manage the most is the chemical properties. So they tend to be a little bit more dynamic. They change more frequently than our physical properties often. So I'm going to start chemical properties like I started physical properties. If you had to know one chemical property about your soil, I would recommend the cation exchange capacity. But this is also something you can get an idea about based on the texture. So cation exchange capacity, that is the measure of the amount of cations that a soil can hold, which are exchangeable for plant uptake. So this is how many nutrients that the plants need that the soil can easily hold on to. How much of that can your soil hold? So how many reserves do you have where you could store nutrients? So a soil with a low CEC might have leaching problems, where if you add a nutrient to your soil, it might not be able to hold onto it for a while in order for the soil to take it up. Or your soil might just be nutrient deficient then as well. So Why your texture can give you an idea about this is that your soil is negatively charged, but that comes from the clay. Sands and silts are fairly stable. They don't really have much of a charge, but the clays are different. They have a different structure, a different crystalline structure to them. And their structure that they have gives them an overall negative charge. So positively charged ions, the cations, will become attracted to them. So they'll hold on to them more easily than, say, sands and silts will. They don't really hold on to much. And they can hold on to a variety of these cations. But they'll hold on to those that have a greater positive charge more tightly than those with a lower positive charge, right? Like stronger magnets almost. So things like calcium and magnesium have a positive 2 charge, and those are both nutrients that the plants need to grow, right? They are essential plant nutrients. So it's great because it'll store those, and then the plant will give off hydrogen to coax off some of those cations that it needs. So there's an exchange of cations. So the plant's usually giving off hydrogen to take some of those nutrients away. So if you add calcium to your soil, and most of what is on your clay particles is sodium, for example, a +1 charge, the clay particle is going to prefer that higher charge on the calcium. So it bumps off the sodium, it lets go of that, and it takes on the calcium, which is good if you have sodium in your soil, because then you can flush the sodium out of your soil if you don't need it. So that's one way to think about how we can change our nutrient relationships in our soil. So because the clay particles hold the nutrients, the more clay you have, the greater capacity you have to store nutrients and exchange them. So sandy soils with just a little bit of organic matter are going to have very low cation exchange capacities, because organic matter can also hold nutrients like this. It's often negatively charged as well. It's actually very strongly negatively charged, but there's a very little amount of organic matter in your soil compared to the minerals. So even a sandy soil will have some cation exchange capacity, but once you start getting into like the silt loams and the clay soils, that's where you have the most ability to store and hold and give off nutrients for your plants, right? So that's what we want, because if we add nutrients to the soil, we don't want to just keep adding them if they're not going to take up all the nutrients. If your plants aren't going to take up all the nutrients, and the rest are just going to wash away. So they act like little storage sites for your soil. All right, another kind of important chemical property that's one that we tend to talk about a lot and can change, right? Different plants like different pHs. So this was one of our questions I think almost everybody got right. What is the chemical property on that list? And it was pH. And pH, if you remember back to chemistry, is your measure of hydrogen ion activity of a solution, or of the solution in soil. So it's how acidic and how basic is it. So the more hydrogen you have in your soil solution, the more acidic it is. So it goes to those lower numbers, which might be something like vinegar is at 3. So that's fairly acidic. Lemon juice is at 2. Coffee 5. So a lot of like the liquids we deal with day to day, or even like ingest, tend to be more acidic. Water should be neutral at 7. And then we have things like soaps and ammonium at the higher pHs. So that's where you have less hydrogen. And instead you're going to have hydroxyls. Okay, so the OHs. So our soils, there are ranges that certain plants like to be at. I once had a student who was on the pineapple diet, right? Do you guys ever like listen to college kids sometimes? It was ridiculous. She was eating a whole pineapple every morning for breakfast. And this was on soil judging. And I'm like, what are you doing? He's like, I eat it until my tongue burns. And I'm like, because it's so acidic, right? You shouldn't be eating that. So we need a nice balance. And I'm like, your body's not ready for that kind of level of acidity. So if your soil acidity changes, your pH changes too far out of whack, the plants are going to tell you, right? So certain plants only like certain ranges of pHs. And there might be like a sweet spot in the middle that they prefer to be at, but they can tolerate certain ranges, like maybe 6.5 to 7.5. And it's going to vary from plant to plant. So what kind of soil pH looks like is in a neutral soil, you have about equal amounts of hydrogens and hydroxyls in your soil. So OHs and hydrogens. And then as your soil gets more acidic, right, you have this logarithmic change in your soil. So you have a much greater increase of hydrogens in your soil. And that content changes very quickly when you go from 7 to 6 to 5, right? Five is fairly acidic. But when you go the opposite way, then you start to lose the hydrogens and they become hydroxyls. So if you remember with cation exchange, your plants are giving off hydrogen to get the nutrients that they want. So in a natural system, right, where you have, say, a grassland, the vegetation dies and decomposes and it goes back to the soil. So in that decomposition process, it's naturally adding some of those nutrients that it took up before. So it's adding some of the calciums and stuff back in. So you don't go too far out of balance over time. But in ecosystems or managed landscapes where you have, say, crop removal, you're not putting all of the plant back. And often you're taking away like the nutrient-rich part of the plant. So this is where pH actually does start to change, is in managed landscapes. And it tends to go the more acidic way because we're not adding as much plant material back in that has those nutrients, those cations that would go back onto the cation sites. But hydrogen is the least preferred of all of those cations. So we can easily add some of those cations and nutrients back in to bump off those hydrogens again later. So really tropical soils as well, where you have more rainfall. Rain, right, is naturally slightly acidic because of the carbon dioxide in it. So they tend to be more acidic because they get more rain as well. So Nebraska is kind of nice. We're on like the cusp of being just slightly acidic in the eastern part of Nebraska. But overall, most of our soils are kind of in the neutral and then to the alkaline range as you get into western Nebraska where there's less precipitation and your parent materials have a higher pH. So your pH of your soil is, again, tied to your parent material. What is the natural pH like? And then the surface can vary depending on how it's being managed. So pH is one of those things that's also kind of nice to know. If you can know it, it's easy to measure because it tells you maybe about nutrient availability. So certain nutrients will be available at different pHs because of how many hydrogens and hydroxyls are available and what kind of bonds are going to form at those different pHs. Toxicity, so there are points. When you get to a low enough pH, usually around 3 or 4, that's an indication where you're going to have a lot of aluminum as well. So aluminum is a highly acidic cation. So you might have aluminum toxicity. That's something you might expect to see down at those really low pHs. It gives you an idea of like what type of mineral or element you might need to use to amend your pH. So, and how much of it you might need. So the more or the further you are away from neutral, the more of something you're going to need to fix your soil pH. Sulfur and lime are the two that we're going to use the most, mostly lime, to bring our soil pH back up from acidic. It can give you an idea of CEC because that ties back to nutrient availability and it tells you how much hydrogen you have in your soil, so how many of your CEC sites might be filled with hydrogen. And then the last two, the range of the pH, where it actually is, will determine what kind of microorganisms are active, how active they might be. Because it's just like us, we like certain pHs in our tummy, on our skin. So microorganisms, they live in the soil, so they can only tolerate certain pH ranges when they're in the soil. Same as the plant. All right, so thinking about nutrient availability. So in general, we have neutral right down the middle of this diagram, so 7. Green is good. That's where you have the high concentrations of those nutrients. And these are all plant essential nutrients in this case. The nutrients that the plants all need, maybe not all in the same amount. The macronutrients, what you need a lot of, are more at the top. The micronutrients are at the bottom. But there are certain micronutrients that are deficient in a lot of soils that we have to amend for. So some of the things you might notice is that at the lower pH range, so to the left where it's more acidic, the macronutrients, those are that are at the top, tend to be more deficient. So you tend not to have as many of those, which makes sense because your potassium, calcium, magnesium are cations that are exchangeable. So those would be missing from your CEC sites and your hydrogens would be there instead, where you have higher hydrogen concentrations. The opposite is true at the high pHs. So now you have more of your micronutrients that you don't need a lot of, or your trace nutrients or trace elements are more deficient at the high pHs. So usually we try and stay like kind of close to neutral, maybe slightly acidic tends to be a good spot for most things, including your microorganisms in your plants. But again, it depends on what you're growing. So some plants do like fairly acidic soils, like blueberries. And I love blueberries. I think a lot of people like blueberries. They're delicious. Grasses also, like, so turf, another one where pH plays a role. So for example, like there's a bunch of different varieties of grasses, but most grasses like to be between 5.5 and 7.5 before you start seeing the nutrient effects because of those different availabilities. So if you're close to that slightly acidic neutral zone, the most issues you're going to have are not really with your nutrients, but more with like disease. So you can kind of control and narrow your window of like your problems that you could have in your soil if you can amend for your pH. So let's see. I have a table in here about what some common ideal ranges are for different plants. So more of like the flowers and the shrubs, that's widely variable depending on what you're growing. So like rhododendrons actually prefer more acidic conditions versus like lilacs and crabapples and dahlias are more on the neutral side of things. Fruits and vegetables, they also tend to like to be like slightly acidic up to neutral, maybe a little bit above that. And then the turf, again, that's a more narrow window as well. So different plants like different pHs. So I'm going to mention this again in a little bit, but a soil test kit from a place like Menards is like $15. And it's really easy. You put just a little bit of soil in a test tube, a little bit of powder, a little bit of solution, you mix it up and it gives you a color rating and it tells you what your pH is. And the kits though also come with usually the ranges for specific plants, a really long list of them. So it gives you an idea of like where you stand and what's ideal for your soil. So rather than amending the pH, which can be a yearly thing depending on your type of soil and what you're trying to grow, you can just change what you grow, right? I know I like lilacs, so I want to keep them. So maybe, maybe that's worth it for me. So I'll keep changing or updating the pH of my soil if I need to. But if it's not, and you want to go with, an easier to take care of thing, you could recommend to growers like try and plant for what your pH is, then you don't have to change it as much. So, and maybe that's not the best option for them, but it is an option, a good recommendation. So, all right. Thinking about amending your pH. Sounds easy, right? Everything sounds easy when I'm just like, oh yeah, you just throw a little bit of this on there and it'll change your pH. Right, there's some math to think about with that. So the CEC provides a problem with that, in that if your soil can hold more nutrients, it's like a parking lot. If your soil can hold more cars, you have more cars to replace if they're acidic and you want to bring it back to neutral. So if you know your CEC, the higher it is, the more resistant to change. So you have to add more to your soil to see those changes. So that's buffering capacity. So the clayier the soil, the more you have to add because it's going to fight that change because there's more spaces you have to fill in. And this is something you want to know when you are applying materials to change your pH. So sulfur would get applied if you're trying to bring your pH down. and lime would get applied if you're trying to bring it back up. So if it's too acidic. So the lime is the one we tend to use more than sulfur, especially in this part of the world, where our pHs, our natural pHs are actually kind of close to neutral or a little bit alkaline. Organic matter is also going to increase your buffering capacity because it can take on a lot of nutrients before it's going to create an effect in the soil. So if you think about sandy soils, if you apply a large amount of a fertilizer or a pH amendment on those soils, the CEC is really low. And you might be like, well, I'm just going to get it all in one shot. If we don't manage it correctly, we could end up washing most of it through the soil before it's effective. So that's a loss of nutrients. It's a loss of money as well. And it could create environmental issues if that concentration is too high down below. So the clay soils are less likely to leach materials through them when they're applied in large quantities. But if you have a really strong rain event and they don't get mixed into the soil, they could be eroded. Yeah, they could be washed away. So we have to kind of think about how we're going to manage it and apply it in our soil. Is it going to be mixed in or just surface applied? And what's the texture like? And how much do we have to apply? So raising your soil pH, that's usually using lime. So it's fairly common and easily available. And lime is really just limestone, which is calcium carbonate. So, this is always one of the best days in class, right? It's physics. It's like Earth's natural, like homemade volcano, right? So it's got a high pH. You put a little bit of vinegar or hydrochloric acid on it, and it reacts. So you have that reaction. So limestone, that can just be harvested from, quarries and stuff. And there's a purity rating on it. So ideally, the higher the purity, the less you have to put on because you don't have other things mixed in there. And most plants, average plants, when we think about crops and fruits and vegetables, kind of want to be around 6.5. So just slightly acidic. And it's the calcium in the lime that reacts with your soil because that's the more preferred cation, remember back to CEC, than hydrogen because it has a higher charge. And calcium is actually a basic cation. Hydrogen is an acidic cation. So you're adding something that has a higher pH to bring up your pH. So it'll bump off those hydrogen ions in your soil, and you add some water and it washes the hydrogens away, but it keeps the calcium. So it adjusts your pH that way. It is better if you can incorporate it into your soil because it'll get mixed in a little bit better, and do it before planting so you don't shock your plants too much ahead of time. So again, this just kind of goes back to a general idea of how much lime you have to put on depending on your pH. So if you're at a really low pH, here we have a 4, it's really acidic at the bottom. A sandy soil might need 10 pounds of lime for every 100 square feet. But the clayey soil, because it has a higher CEC, it can resist the change. It needs over twice that amount. So depending on your area that you're working with, if it's like a small garden, that you might still just be within a bag or something of lime. But if it's a very large area, it can add up really quickly depending on your texture. All right, so you can see those differences throughout different pH levels. So the further away your pH is from where you want to be, the more material you have to add, and then that gets compounded by how much clay you have in your soil as well. All right, so same principle with lowering the pH, except now we're going to use sulfur. So we use the sulfur to reduce the pH, again, usually to about 6.5. Same thing though, it's going to depend on how far away your pH is from where you want it to be, what your CEC is like, and also the amount of calcium carbonate in the soil. So at high pHs, you tend to have a lot of that natural lime in your soil. For those of you out in western Nebraska, that might be a little bit more apparent closer to the surface. And it looks like white nodules, white masses, or even streaks in your soil. If anybody in eastern Nebraska has a till soil and you dig down deep enough, you might see those white streaks as well because there's carbonates in the till. If Terry lets me take you off campus on field day, I know where we can go see some carbonate. Oh, it's great. We'll talk about that. But anyway, it's really hard to get rid of those free calcium carbonates because they've accumulated into masses. So they can be hard to break down with sulfur. So that just makes it another issue. This again, it's better to incorporate it into the root zone to get the best results because you just want it to be where your plants are going to be, especially if it's difficult. So again, if you're just mostly amending the topsoil, it's not like you have to go very deep in your profile to do the mixing. And then we're going to see a similar relationship. So again, we're usually trying to get to 6.5. That's our good average kind of pH. And the further you are away from that, the more sulfur you have to add. And again, the more clay you have, so the further to the right on the table, the more sulfur you have to add as well. So if you have something that's like a medium textured soil, that's great because you don't have to add too much. You don't have to worry about it like just washing through your soil too quickly or over applying it. And you know that that's a good texture for your plants for water holding. So we're not all that fortunate, I know. Clayey soils, I tell you, one of these days. All right, so I already made a plug for this. We might get a couple of these for the field day this summer and play around with one. But the soil test kits, they look small, but they're very powerful. I bought one of these last year for the group and we did a bunch of tests. So the little soil test kits, they can give you a good simple picture of what's going on, like in your gardens, or you can recommend them to folks if they're just trying to get an idea. So they're usually like $15. I think I bought it for $14 last year. And they'll usually test for pH, and then nitrogen, phosphorus, and potassium. So the big three nutrients we're usually fertilizing for. So it has a variety of solutions. The instructions are very specific, and it has a couple of test tubes. And something like this, it's not just one test of each. I think this one, we could do 40 tests. So you basically got 10 of each one if you wanted for these different tests. So like for my garden last year, I got excited. So my garden's not that big. It's maybe like 30 feet by 15 feet, and it's 2 levels. I did 8 pH tests on my samples because I'm a soil scientist and I'm bored on the weekend. Did I need 8 pH tests? No. 1 would have been fine. I could have used 1 sample, but I just kind of wanted to see how much variability existed along the length of my garden because it was long. And I just wanted to see how well it worked. So I wanted to see how consistent it was, and it was actually fairly consistent. But it's great because you just mix the tube and it's ready results. They color change and they provide color codes with it. And then they give, again, recommendations and guides for the pHs, the nitrogen, phosphorus, and potassium you want for different plants. So it kind of tells you where you want to be if you want to grow a certain plant. And then it tells you where you are. So this is great for, just some simple tests. If you want a better suite, something that's more specific and you don't want to do, the mad scientist on the weekend, you can also send soils to a testing facility. And this is maybe good for like every 5-10 years to get a good kind of solid picture of what's going on. But the problem is that these are $15 to $20 per soil sample. But each soil sample will have a suite of things. It'll tell you your texture, organic matter, pH. It'll tell you your CEC, what your ratios of hydrogens and calciums and sodiums are. So it gives you a more detailed look at your soil. It's just a little bit more expensive. But what they usually recommend is, we'll get to this shortly, when you send in a soil sample, if, like we're in a classroom, if this entire classroom was one garden and there's not a lot of variability in our soil, like we don't see a lot of difference in texture or how our plants are doing from one corner to another, we can grab a little bit of sample from a couple different spots and just put it all together because it's one average sample. It's when you have variability from spot to spot in a place that you want to send separate samples. So if you have a lot of variability, that can get expensive. The most common labs that I know of are Ward labs and Midwest labs. And they're pretty quick, and they will actually, for some of your plants, tell you like what your nutrient requirements are in some cases, if you tell them what your plant is. They also do, I think sometimes they do plant analysis too. They might tell you what your nutrient quality is in your plant. Your extension offices might know of more local places, like if there's a community college nearby that does soil testing, or other regional labs as well. So they're great places to kind of reach out to as well. And this brings us into fertility. So I'm going to guess that as master gardeners, these are the questions you get the most of, right? And I mentioned this earlier. I am from a background that is more on the geology side of soils. So fertility was not something I came into early in my soil science career, but it's something I had to learn very quickly and master very quickly to teach other students about. So the unfortunate side with fertility is it tends to be math, right? And I kind of provided you with some example problems that we can work through. And fertility is something, fertility is something we tend to manage quite a bit from year to year. There was a question at the beginning about fertility versus productivity. The physical properties kind of cover productivity, how much light and air and temperature is available for your plant, and water. Fertility is just looking at the nutrients. So that is a component of productivity, but they're not the same thing. So your fertility is just looking at how well stocked with nutrients is your soil and how can it provide those nutrients to your plant. So I don't recommend putting your nutrient pellets right next to your plant, but it's kind of a good photo to talk about, I guess. All right, so plant nutrients. We're probably more aware of these than we really know, but there are 17 essential plant nutrients. We tend to manage for some more than others, and it can also vary by the plant species as well. So carbon, hydrogen, oxygen, those are within the plant, but those are part of the dry mass of the plant. And that's going to come from air and water. So they get those. They don't get that from the soil. About everything else, 5% of the dry weight is coming from the soil. But there are 14 elements in there that come from the soil and that they have to get from the soil in order to grow. So being essential nutrients means that they are required for plant growth and you can't substitute something else for that nutrient. Macronutrients are those that you just need larger amounts of those for plant growth than you do the micronutrients. So for example, nitrogen is the one that they need the most of. I forget the specific weight, or what the units are, but it's like 2,000 compared to, I think it's like copper is like 0.2, right? So it's vastly different scales. I can't remember the unit on that exactly, but largely different amounts. So the macronutrients, they need a lot of that nutrient to perform that function in order to grow well. So, so oxygen, carbon, hydrogen, those are macronutrients, but they come from the air and the water. So we kind of just ignore those. Those are going to be there for the plants. The ones that we need to pay attention to are nitrogen, potassium, magnesium, phosphorus, calcium, and sulfur. So those are big macronutrients. The micronutrients, depending on what you're growing, right? I know some plants like roses are pretty fickle with some of their micronutrients. So our micronutrients are iron, boron, chlorine, manganese, zinc, copper, molybdenum, and nickel. So they tend to be the metals. And they might only need a little amount of them, but if they're not in the soil, that's a problem, right? So we have smaller doses that we use to apply to the soil for our micronutrients than we do our macronutrients usually, but they're still important to kind of pay attention to if you're lacking it in your soil. It's also then easier to have too much of your micronutrients in your soil compared to your macronutrients as well. So again, ice cream and chocolate, more is better, unless you can't eat ice cream, and in that case, my heart hurts for you. I grew up in the dairy state, so ice cream is like its own food group for me. So not more is better is the case with nutrients, right? Because the soil can hold a lot, but the plants only need a certain amount. In that case, sometimes it's just too much and it's going to hurt your plant. So again, essential plant nutrients are required for plant growth, reproduction. Nitrogen is required, I think, for making, Terry, you can correct me because I'm going to get it confused, making DNA. And then I know phosphorus is necessary for good root growth, making proteins. And potassium is good for hardiness and good root growth as well. But there's natural plant functions in there. I am blanking on them. So it's a good thing I don't teach this for like 2 weeks in my class. I'll remember it before then. So in some ways, like you can see it in certain molecules and like they'll have very distinct reactions on their leaves and tell you when they're deficient. But usually by that point, that's a problem. So we want to get there before that actually happens. So taking a soil test before you plant can help with that. All right, so nitrogen, phosphorus, potassium, those are 3 of the big macronutrients. Nitrogen is needed in the largest quantity of all of our nutrients. Phosphorus is not needed in as large of a quantity as potassium, but it's harder to get in the soil. So it kind of bumps up in its level of importance with fertilization. So those are the big 3 that the plants use a lot of, and that it changes frequently in the soil. So they're a little bit more dynamic. So things like vegetables, they need high amounts of those to grow because they grow quickly. And we're harvesting them pretty regularly. Lawns are kind of like a medium to high. You notice like we tend to put on more nitrogen for our lawns. The nitrogen gives you that like nice dark green color to most plants. Herbs are kind of on the lower end. They're a little bit more self-sufficient. And then fruits and flowers, they tend to be more on the medium side. And then trees, shrubs kind of tend to be medium to low. So they're used to those more acidic conditions, I want to say, than say some of the others, which need a lot of nutrients to keep growing. And that's good though, because more permanent structures like trees and shrubs are hard to manage when they're already in the ground and they're fairly large, because you can't do a lot of digging around them. So it's good that they don't need as many of those macronutrients as some of the others. So. All right, so when we go and buy fertilizer, there's a lot of things on that fertilizer label. And a lot of it is numbers, right? So the numbers we tend to pay attention to are the grade at the top, which are 3 numbers separated by dashes. So in this case, 4, 2, 2. And that tells you how much nitrogen, phosphorus, and potassium are in your soil, in that order, always in that order. So in this case, we have 4% nitrogen in our soil. We have, fertilizer, excuse me. 2% of our fertilizer is phosphorus and 2% is potassium. Down here in kind of like the ingredients, it tells you exactly what the form of that nutrient is. So in case of potassium, it's potash, right? And phosphorus, it's in the form of phosphate. So those are the most common forms it's going to be found in. So as a percent, the way to think of that is if you had, this bag is only 4 pounds. If this bag were 100 pounds, 4 pounds would be nitrogen, 2 pounds would be phosphorus, and 2 pounds would be potassium, right? So that it's a percent. So you think in pounds of 100 or bags of 100 pounds. So if you don't have 100 pounds, you have to do a little bit of math to figure out, well, how much nitrogen, phosphorus, and potassium is that? Looking at your labels is important. There's always some micronutrients in there as well. So you kind of want to take a look at like what's all included besides nitrogen, phosphorus, and potassium. So complete fertilizers are those that have a little bit of all 3 of those, and they might have some other components as well. But in a lot of cases, maybe we just need 1. We might only just need nitrogen, just need phosphorus, just need potassium. So there are single nutrient fertilizers, or primarily 1 nutrient that we can get in a fertilizer, so that we can just apply that one without over applying the others. And then you can get different types of fertilizers. So slow release, those tend to be more organic fertilizers. They are coated. They're less likely to burn, maybe some seeds, less leaching, that they'll release slower in your soil. But they tend to, respond to differences in moisture. So you might have to keep a consistent moisture content in your soil. The fast release ones tend to be more inorganic. They are more likely to harm a seed or even some roots, but they tend to be less expensive. So you kind of get a quick reaction in your soils from that. So depending on what you're growing, if you want a little bit of fertilizer coming out throughout the year, maybe slow release is okay. If you have an immediate problem, maybe a little bit of fast release and a little bit of slow release to feed your plants throughout the year. So some examples of some organic fertilizers. I know, just out of preference, we try to use organic fertilizers as much as possible around our house because we have a lot of bees in our neighborhood too. So we try and keep it as friendly as possible over by us. So things like bone meal, cottonseed meal, oh geez, blood meal, fish emulsion, sewage sludge is organic. Manure, compost. When you start to get to things like manure and compost, the ratios vary depending on what goes into it. So, for example, when you go get compost at a city landfill, for example, for free, right? You just pay to go in. You don't have to pay for how much you take. You don't really know what the ratio of nitrogen, phosphorus, and potassium is because you don't know what went into making that compost. So if you have more control over it, then you'll have a better idea. So example, blood meal is really good for supplying nitrogen and not the other two. So if you just need, a punch of nitrogen in your soil, that's a really good one to use. All right, so fertilizer calculations. It's not that hard, right? It's great that we all have calculators on our phones now, so we can do this in the store. It's awesome, right? You gotta be that person, right, at Earl May on your phone, like, I'm not looking something up, I'm just trying to do my math. I can't remember how to do it. So fertilizer calculations, if you have a certain plant and you wanna have a certain amount of nitrogen in your soil, so say you did the NPK test with your soil test kit, and it tells you how much nitrogen you have, right? You can go get a nitrogen fertilizer and it tells you how much nitrogen is in there. Now you got to do a little math to figure out how much you actually have to apply. So it's great to do your test first so you know what type of fertilizer to buy, complete or single, slow or fast. And then you would determine how much you add based on what you actually need so you don't over apply it. So I sent a handout for Terry to give to everybody. So there's a couple of different ways you can do this. And maybe we'll do a couple of examples just to see how everybody's doing and try and do the math together. Because I think the rest of this is going to go pretty quick. So I have two equations and they look really similar. It just depends on how you use your percentage of nitrogen or phosphorus or potassium in your phosphorus or in your fertilizer grade. So first equation is figuring out the total amount of fertilizer or material. I think, yes. Oh, the nutrient in a material. Sorry, I was reading something else. So you're calculating the amount of a nutrient in a material. So if you have a grade that is, for example, 18, 46, and 0, and you want to know how much phosphorus is in that material. Well, you know that for every 100 pounds, 46 pounds is phosphorus, because 46 is where the phosphorus number is. But we have 500 pounds of that fertilizer. So we would take 46 and divide it by 100, right? Because 46 pounds for every 100 pounds, multiply it by 500, right? So if we're trying to figure out the amount of a nutrient in the total fertilizer, one way to check your math is if your nutrient is less than 100%, the amount of your nutrient should be less than the total amount of fertilizer you have. If it's the opposite way, you're doing it wrong, right? You shouldn't have more than 100% of your fertilizer as one nutrient, because in that case, that's magic. And I will invest in that right there. Okay, so that was the first example. So it's just kind of looking at, well, if 46% of your material is this one nutrient, what is 46% of your total amount? So there's a couple of examples to work with. One thing I want to point out is for compost and grass clippings in your first table, it just lists the amount of nitrogen as a percent. So you don't have to do like any conversion with it because 46 was a percent, right? You can just imagine that with compost, for every 100 pounds, 0.8 pounds is nitrogen. That's very different than some of your other fertilizers. And that's a common problem with organic fertilizers, is that you tend to need a lot of the material to get the nutrient out that you actually want. So, okay, so then the second part is calculating the amount of a material you need to get the specific amount of a nutrient that you want in your soil. So this tends to be the equation we use the most. Right after we've done our soil tests and we figured out our fertilizer. So for the example of the first one, we know we want to use or get out some potassium. I guess we need nitrogen and phosphorus. We've already checked that. So we're going to use this mixed fertilizer that is 7-12-7. And from this, we need to get 40 pounds of potassium. Okay, so now we need to figure out, well, how much fertilizer do I have to buy to get to that point? So if you look at the example equation now, you take your starting mass that you need for your nutrient, which is 40, and you multiply it by your ratio of 100 pounds to 7 pounds, except this time you flip the position of the 100 and the 7. So you're just flipping your ratio of where those two numbers go. So the way I like to think of these two equations is in the parentheses, your pounds of a nutrient to 100 pounds of fertilizer or compost, whatever you're working with. Whatever is on the top part of that equation is the component you're solving for. So if it's the nutrient is on the top, you're solving for the mass of the nutrient. If it is the fertilizer on top, you're solving for the total mass of the fertilizer you're trying to get. Okay, so it's a similar equation, but it just works a little bit differently. So those are kind of straightforward. There's an example on the back, which is way more applicable and my students hate doing. But I believe in you guys, right? You guys got experience. You got this. You know how this is gonna go. All right, so it's actually pretty common that, you know, a complete fertilizer has a little bit of nitrogen, it has a little bit of phosphorus, it has a little bit of potassium. You can search all you want. You are not going to find the magic fertilizer that meets all of your needs with one material. So, and we often have several things to choose from. So in this case, we need a certain amount of nitrogen, a certain amount of phosphorus, and a certain amount of potassium for this longer example. And the way to start approaching that is we have 2 mixed fertilizers and we have 2 single fertilizers as options. So we'll start with the mixed complete fertilizers. And if we look at how much we need 4 pounds of nitrogen, 1.2 pounds of phosphorus, and 3 pounds of potassium. So you're kind of drawn to the first one where it has, the nitrogen is needed in the most, so it has a high amount of nitrogen. Then the potassium, so that's 12, and then the phosphorus is the lowest, so 3. So it kind of has a nice balance just looking at the numbers. So where you would start is you would start to figure out how much fertilizer you need based on what you need the least amount of to avoid over applying. So you start with phosphorus because you only need 1.2 pounds of phosphorus. So you would start with equation 2 to figure out your amount of fertilizer because we know how much nutrient we want. Now we want to know how much fertilizer does that mean. So if we took 100 divided by 3, right, because we have 3% of our nutrient is phosphorus, multiply that by 1.2, we get 40 pounds. So to meet our phosphorus requirement, we would need 40 pounds of this fertilizer. Okay, so now we're not going to stop there. We need 2 more nutrients out of that fertilizer. We don't want to over apply them. Too much nitrogen creates groundwater issues if it's applied in too much. And it's just not good to over apply and kind of waste the nutrients. So now we're going to jump back to equation 1. So you kind of keep going back and forth to see, is this too much or is this too little? Do I need more from this material? So we have 40 pounds of fertilizer. Now we can just go with nitrogen. It doesn't matter which one we start with. So using equation 1, how much nitrogen do we get out of 40 pounds of fertilizer? So 20% of our fertilizer is nitrogen. So now we take 20, right, divided by 100, and multiply it by 40. And we get 8. So if we apply 40 pounds of our fertilizer, we get 8 pounds of nitrogen. That is double what we need. So you're just like, stop, it's too much. We cannot use that. But hey, we have another complete fertilizer. So you start all over with that one. I know, you got to start the math over. And what you'll find is that this one will work. It doesn't get you all the way to where you need to be with nitrogen and potassium. So that's where the single fertilizers come in down below. So you see there's one that's 3100. So that's just nitrogen. So you'd fill up the void space of what you don't get from that complete fertilizer with your single fertilizer. Same thing with the 0050, that's just potassium. So you kind of are making your own customizable mix with a complete fertilizer and a little bit of each of the single fertilizers, okay? I know, it's almost 9 o'clock and I was doing math at 8 a.m. this morning, so I get it. Take it home, right? If you want to talk about it, email is great. I am completely open to looking at it later, but I just kind of wanted to walk through some of the steps of what you're going to see when that happens. And it's one of those things where like you do get frustrated and it's just like, I can't find one thing to make it work perfectly. So I like things to be as easy as possible, but it's a little bit of recipe. It's like making your own cookies, right? Except they're going to be beet cookies or beet cake and zucchini bread. It's all going to turn out wonderful in the end. So, okay. So how do we know if we have enough nutrients in our soil, right? We take a sample. We test it beforehand, so we're not just willy-nilly throwing stuff on the ground. So there are lots of videos out there that you can watch to see how to do soil sampling. And I kind of touched on this already. A shovel or a spade is your friend. Trying to keep your volume as consistent as possible if you're sending a sample in, and it's going to be a mixed sample. So this is kind of what I was hinting at a little bit earlier when I was talking about when you send in a sample to a lab. Because your sample is like $15 to $20 per sample, you can mix your sample if it's coming from a fairly homogeneous area, whether it's being managed one way or if you think the soil is pretty much consistent. So, for example, if this were a piece of property where you have a front yard that's on the north side, so it's a little bit more in the shade, your backyard is on the south side, so a little bit more in the sun, you might have microclimate differences. You might have different plants that thrive better. So I would do, a couple spots and grab a little bit from each one. Try and grab the same amount in different spots in your backyard. And that's one sample that you send in. Your vegetable garden, you're going to manage that differently. Different types of nutrients and fertilizers you put there. So again, grab a couple of consistent volume size samples, mix it all together, one sample. So that you're not sending in like 50 samples from across your yard. You're sending in 4. Instead, right? And you'll get just like an average for an area. If you notice, like within your vegetable garden, there's one spot that just for some reason You can't get anything to grow there, but it grows everywhere else. That's one where you might be like, I'm going to send in a sample just for that one spot. Okay. Or if like you can't find a difference in the home test kit, maybe send that one sample in to see what the problem is. So what kinds of things to consider when you're doing it? Where your subsamples are coming from. You want to try and capture the variability within your fairly homogeneous area. So try and get, kind of the wet spots and the dry spots, and where you think you might have good plants or bad plants growing. No plants are bad. They're just not as robust, I want to say. They're just not in it, right? They're not giving it all they got. And then sending in one kind of mixed sample for an area if you just want to get a glimpse as to what's going on in that section. Depending on your area, I don't know how many acres of land we're all dealing with, but we generally recommend, like, if you're working with something that's like 20 acres, you want to grab like 15 to 20 subsamples, so handfuls, to put in there and mix together, because that'll kind of capture the variability with that. Smaller spaces, it's up to you. I like to send in like a quart-sized bag of soil. That's about it. Just enough that you can like squeeze the air out of it, so a little bit of space in there. And it is best if you do send it to a lab, even with your home test kit, it should be air dried before you do something with it. The depth for gardens and turf, about 4 to 8 inches. So you want to kind of capture where the roots are going to predominantly be in your soil. And then there's a lot of NEB guides out there that kind of describe certain depths or how to do sampling for different things. And depending on what you want to send it in for too. So some soil tests require certain depths. Like nitrogen is very mobile in soil. So if you want to see if you've been over applying nitrogen, you could try and dig down deeper and see if there's nitrogen deeper. Because if there is, that tells you it's been washing through your soil and it's not being held or taken up by your plants. And then just kind of keeping a consistent volume. So if you're grabbing several subsamples, use like a spade and try and get like the same cup size or handful size for each one. So you don't get, one high pH spot, one low pH spot, but you have one big sample from one and a small sample for another, because it won't capture all that variability correctly. It'll kind of skew your results a little bit more. And then just kind of consistency with each subsample, maybe just brushing off the spade before you go to a new area, that sort of thing. Again, lots of NEB guides out there that talk about guidelines for sampling. Again, it kind of has another diagram on it on this one on the left about, if you have little microclimates because of structures. I know we have the example I was talking about where our backyard faces the south, so it's sunny, but then there's a tree, so half of our backyard is in the shade. And then the front, that's facing the north, and that's in the shade almost all day. So I would almost do 3 separate areas within my one kind of yard-ish area. All right, so common problems in our soil that we tend to talk about the most, right? Because this is really what you came here for. What do I tell people to do? I'll be like, things. They're gonna do things to their soil. You might notice this is one of my favorite photos when I talk about soil, and it just kind of shows you what happens with erosion and can happen kind of quickly. Is you can get kind of like little cut banks in what used to be flat after a particularly wet year. It's not as flat anymore. So your location is going to be important, and then thinking about like, what is your climate like? Are you more likely to have erosion, deposition, that sort of thing? Like, what's going to be affecting your landscape and where you are? So urban areas, that's a whole different ball of wax compared to more rural areas, because you have a lot of impermeable surfaces where water doesn't move through it. So roads, sidewalks, driveways that you have to contend with and that your plant roots are contending with, right? So trees hate driveways and sidewalks, and I don't blame them. I mean, I would not like them either. So the rough part about those impervious surfaces is that it increases runoff. and soil temperatures as well, especially if it's blacktop, right? So it's going to absorb that heat and it makes it warmer where your plants are. So they can be a little bit too hot in that case. Heavy equipment like construction equipment, concentrated foot traffic, you're going to get compacted areas as well. Prime example is on East Campus, on the other side of where we currently are right now. If anybody comes to Lincoln, go visit Hardin Hall on the corner of 33rd and Holdridge Street and go around to the north side and you can see where the students walk and it's not on the sidewalk. There is a permanently beaten down trail across the grass because it's faster to go through. And a lot of students, I've advised a couple of seniors in their thesis projects and they've measured the compaction and it is compacted and it's just students walking over it every single day. So plants will not grow in that area anymore. We also have removing and not replacing topsoil, like with construction. So cutting it out to make it level, putting up some buildings, and that's going to change your drainage. So the subsoil tends to be denser, smaller pores, clayier. So now you brought that to the surface and it doesn't have organic matter. So the water doesn't move through it as easily and it's more likely to erode. And now you've changed your fertility, right? We've taken away that nice nutrient-rich organic layer and now we have to start all over again. Chemical spills, these are more common in some areas than others. I know there's a lot of Superfund sites, surprisingly in Nebraska from like the munitions plants and machinery plants and stuff like that. So thinking about like what goes and what could have contaminated a soil. So especially in your older houses, maybe testing the soil around the house for lead paint could be a good one as well. And then just kind of like dumping or burying waste materials. So I know we found the old outhouse in our backyard and we were putting it in our garden. So yeah, that was interesting. It was mostly like where they threw the clinker and the brick to fill it in afterwards, but there's a definite spot. And you're like, well, that's going to be a tough fence hole post to dig. And it was. So, you just have a lot more variability to deal with and different kinds of problems in urban areas. The biggest one is the soil compaction because we tend to walk over it to get to where we're trying to go. So trying to keep like separate spaces that you only walk on is great. Mixing it up if you need to, like tilling it and replanting it in grass and then avoiding it for a while. Because you're going to lose your pore space, you're going to decrease your water infiltration and your aeration and your drainage. And that does affect your soil temperatures, which can affect your plant hardiness as well. The wetter your soil is, the less likely it is to change temperature. So it heats up more slowly in the spring. So it can take longer for your plants to germinate and start to grow. So what were some indicators? We kind of talked about a couple of these already. So hard soil, it's hard to dig through. It feels like a rock. Platy structure, so if you can dig it out and it looks like a flat sort of book almost. Standing water is another good one because your water is not moving through your soil if it's compacted because there's not enough root space or pore space. Or runoff. If it's just a little bit of a slope and rather than going in, it's mostly just moving off. Poor plant growth is another one, so plants tend not to grow in that space. If you can measure it, your increased bulk density goes back to your hard soil and your standing water. So you're losing the pore space. You're filling more solids into a volume of space. And then surface crusting, which you might see with the standing water. So the particles tend not to have those aggregates and it's just a flat crust. Some surface crusts, though, are not necessarily from compaction, but from excess sodium. So if you see a crust that has like a white buildup on it, that could be an indication that you have too much sodium in your soil because it's doing the same thing. It's dispersing your particles. In that case, how you fix a salty, I guess, salty and sodic are not the same thing when it comes to soils. So sodic, sodium-rich soils, you fix with gypsum because the calcium pushes out the sodium with that cation exchange. And then you'd have to leach it out. And that takes a while because the water doesn't move well through that soil. So Solutions, right? Easier to avoid compaction than to fix it. Just avoid repeated traffic and walking, especially on wet soils. So wet soils are a little bit looser, they're a little bit weaker, so they compact more easily into that pore space. Altering maybe some circulation patterns, how you walk on the soil, what plants you grow where, aerating it once in a while, that's pretty common for lawns. Adding some compost, because that'll like help improve your structure. Water will get added into it, kind of like, it's like a sponge growing almost when you add compost and you wet it. And then if you're in an area where you can till it to kind of loosen it up, but just not excessively, because that's walking over it repeatedly again and again. But that's a good way to kind of loosen it up for, say, gardens and stuff like that. Excessive moisture and drainage. This was a problem this last year. I know I gave Terry a picture of my gooseberry plant, and I'm like, what is killing my plant? Do I have a bug? And she's like, no, you don't. It's just been a wet year, and my plants were not accustomed to that. So this is going to be more common in areas where you have maybe like higher water tables, where you have more ponding of water, or you have conditions where water doesn't move through your soil well. So like compaction, high clay content soils. It could be due to like improper construction methods. So a berm was put up, for example, in some place, and it's going to block the flow of water down the slope. And it just starts to build up there, or just different management practices that aren't great, like overwatering. If you have a high water table and really wet conditions, your roots tend to stay pretty high in your soil. So you don't get well anchored plants, and they're less likely, or they're more likely to tip over. You might get more tree throws as a result. And then having too much water in your soil creates low oxygen and air levels, so you don't get as much respiration for your plants and your microorganisms. So decomposition and soil, or plant exchange processes tend to be a lot slower. So poor drainage indicators: erosion, a lot of runoff, standing, puddling water, odors, right? Moist soil is good. Fishy, sulfury soil is not good. Right? There's a range of soil odors. When it starts to smell bad, it is bad. Poor plant growth, moss, browning of the leaf edges can be all indicators that it's not draining very well. So again, if you don't think it's draining well, you can do that infiltration test where you can put in the ring and see how quickly your water drains through your soil. It's kind of a fun one. You can do that with kids. Oh, it's like the quiet game almost. Oh, that's a great idea. Oh, I'm going to get my friends' kids to do that. Watch the water go down. Some other ones are similar to compaction. So just aerating, adding pore space to your soil. So compost, organic matter is great because it helps improve the structure. So it gets bigger pores, macro pores. So those, highways of water movement. Renovate the space could be another one. Installing some drains, maybe some raised beds. So if you have a really clayey soil, it's going to be hard to amend. Put up a raised bed and put something a little more nicer in your raised bed that'll drain a little bit better. And then just talk to folks about, good management practices like we've been talking about here. Again, drainage test. If you don't want to buy a ring, you could dig a hole. That's another great activity for kids that are bored. Dig a hole about 8 to 12 inches deep, kind of a nice big circle. You fill it with water and you time it. So drainage is good if it drains from the hole within an hour. Fair if it's several hours to a day. Poor if it's standing water. A fenced hole post digger works great for this. We were kind of doing this as we put up a fence this year. And you could definitely tell where the clayey spots were in the fill in our backyard. So this is kind of a fun thing to do, if you have to do something tedious, like put in a fence. Or if kids need something. I'm always a fan of that, right? They get bored so easily in the summer. Okay, so Nebraska is also unique in that we have saline wetlands. We have a surprising amount of salt in this state, it's great. It keeps things interesting, but it can be a problem with your plants. salinity, not sodicity, not sodium, but salinity. So really kind of soluble salts in the soil that are made up of more than just sodium. They're actually fairly easy to fix. It's just a lot of leaching. So because they dissolve in water, you just keep adding fresh water, non-saline water to the soil, and it'll wash the soil or the salts out of the soil. There is a measure, this electrical conductivity. This is one of those values they give you on a soil test from a lab. And most soils are going to be kind of in the less than 1. So your plants really aren't going to be affected by the saltiness of the soil. But because we do have saline areas in Nebraska, especially near the saline wetlands in eastern Nebraska, it can get kind of high. So you might see differences in plant species. So if the salinity is not something you can fix easily, that's one where you want to look at what's available and what can tolerate different salt contents. Because sometimes leaching the soil of the salts in the soil is not easy if your groundwater table is high, because they'll just kind of stay there. So, you know, there's problems associated with each one, but in general, it can be kind of easy to fix if you need to. All right, so I have one more Slido to do. It's just a couple of problems to kind of see what we think. It's 4 problems. So they are like, which of the following would you expect to have this? Or sure, yeah, do you guys want to do them afterwards? Okay, I think it's my last thing anyway. Do I? It's just summary of like all the good things that we talked about. So like the best management practices, but yeah. Yeah, I just had some erosion photos to kind of show, so we'll go over those real quick. Right, these are like the extreme cases of erosion we tend to see in urban areas, especially when we build structures. So, right, you have an impermeable surface. So those can be harder to fix, but if you can plant structures there, even it out with some steps, that would be great. So keeping ground cover there, terracing if it's steep enough, controlling drainage so you don't get water just moving over bare soil. And then also low flow irrigation, because the rain splash, overhead watering on steep surfaces increases your erosion down the slope because of that impact of the watering. So my last slide is just kind of those best management practices that I know we probably tell a lot of like people that ask us about recommendations over and over again, but it really is just, it's those simple things like, you know, taking a look at your soil, thinking about how you're irrigating, reducing erosion. So vegetation over any bare areas is great. And then just being mindful about fertilizing, because we don't want to add too much, but we want to make sure we're getting our plants the right amount that they need. But they like us because we like them. Plants are great. So, all right, that is it. I know soils is a lot to get in one day. So, yeah, hopefully this stuff is helpful, especially the fertilizer calculations. I know I wish I had something like this, like when I was in an intro class. It would have made life a lot easier when I was, you know, practicing my green thumb as a younger person. So, yeah. So I hope to see most of you on the field day in June. I'm pretty excited. I get excited about soil. Just wait till you see me outside talking about soil. Like, oh man, it's hard to contain the excitement. So, anyway, yeah, if you guys have any questions after this, you can shoot me an email anytime. Yes, it is R Young, like age, RYOUNG at UNL. I keep it pretty simple. And I'm sure Terry can pass that around as well. Or maybe I can put it on the screen real quick. We'll make this guy real small. Whoops, not RE. There it is, R Young. Oops, I guess I can't make that any bigger. Anyway, yeah, if you guys are familiar with Zoom and you want to chat, look at some pictures, I am totally down for that too. I think it's great. I teach online, so I'm talking to people on Zoom all of the time. So yeah, any questions, pictures? You want me to check your math? I'm good at that too. So I got plenty of experience. And I'm not too harsh on the math either. So, all right, you guys have been great. Have a good rest of your day, your night. I'm going to turn off the mic because I'm running out of speaking volume. Yes, you're welcome.
Thanks, Becky. So just to remind everybody, June 16th is when we're doing our